graduate student at UC Santa Cruz and part of the pre-doc program at the CCA, is using a suite of cosmological zoom-in simulations, the FIRE2 simulations, I'm sure many of you are familiar with. So these are halos ranging from 10 to the 10 to 10 to the 12 solar masses with fairly high spatial resolution and what I would call sort of semi-resolved prescriptions for stellar feedback. So that when they give talks, they claim that they have not tuned their recipes to match observations. I will leave my statement there. And in these particular simulations, there's no black holes and no black hole feedback. Okay, so when we do the SAMs, we just switch it off. So what Viraj has done is to take a dark matter only version of the FIRE simulations and extract a merger tree, just like the ones we normally use for SAMs. So now we can run our semi-analytic model in the same merger tree as what the simulations are reflecting. For now, what I'm showing you is only for the main branch of the central galaxy in the halo. And what we've done is to measure lots of global galaxy properties like stellar masses, gas masses, etc., as well as what I'll call flow properties, so rates that material are flowing through these different scales. And so the scales that you'll see later on, I'll call ISM scale, which is within 1/10 of the virial radius. These are all arbitrary, of course. We can actually do this for any radius. CGM, which is going from basically through the virial shell and then outside the virial shell. Okay? So I'll talk about halo inflows, CGM inflows, and ISM inflows and outflows. So we have 5 halos that are around 10 to the 10 solar masses at redshift 0, 5 that are 10 to the 11, and 3, I think, 3 that are 10 to the 12. We just got the 3rd one recently. So we don't have many halos. And these are color-coded. So the 10 to the 10 are blue, 10 to the 11 green, 10 to the 12 red. And what Viraj has plotted here is the prediction for the central galaxy made by the SAM divided by the prediction that was made by the full FIRE simulation. Okay, so this is for stellar mass, the cold gas in the ISM, the gas in the circumgalactic medium, and the star formation rate. And these are horrible plots. We're sort of struggling with how we represent this information in a more aesthetically pleasing way. But
it's clear you need logs.
If you put up with that and squint at this, you can kind of take away that the stellar mass actually agrees, it's not too bad. But the SAMs always have, or nearly always have, too much gas in the ISM, too little gas in the CGM, and star formation rates that are too high. And what I really love about this analysis, yes? This is log base 10, I believe. I didn't make the plot, but I think it's log base 10.
Define too bad. It's not too bad.
The stellar masses?
Yeah, this is 5% free.
Yeah.
Is that not too
I would call that not too bad. I mean, different simulations degree at that level, I think, pretty routinely. It's not as bad, right? It's not 2 orders of magnitude. Everything's relative.
Excuse me.
Yeah.
Intuitively, when you increase the mass, seems like you have better agreement.
Yes, you're absolutely right.
So why is like that?
Yep. Let me come to that. So yes, there is better agreement for the more massive halos and much worse agreement for the lower mass halos. So what I was about to say is that one of the things I like about this analysis is that we can diagnose why this is through these flow quantities. And so what we see is that in the SAMs, in the low mass halos, and you can see a trend here with mass, more material is flowing into the halo in the SAMs than in FIRE. More material is flowing into the ISM. More material is flowing out from the ISM. And guess what? In the SAMs, we tune the feedback to match the stellar mass. So, we had all this stuff coming in, and we just threw it out again. Because that's what happens when you tune. And more material is flowing out of the halo as well. So here's another plot, which I have to walk you through. So this is showing the ratio of the rate that gas is flowing in to the halo divided by the rate that dark matter is accreting into the halo. Okay? Now, SAMs assume that these are very closely related. And indeed, empirical models commonly assume that these are closely related, right? That when dark matter flows in, gas flows in. Each track here is one of these halos, and you can kind of read the halo mass off. So this is halo mass, log halo mass. And then the color coding shows you the time along the track, going from the Big Bang to today. And what you can see is that in these low mass halos, this assumption is very badly violated. So dark matter is coming in, but no gas is coming in. Very little gas is coming in. So and we don't fully understand, obviously the stellar feedback is somehow preventing the gas from coming in, but it's very surprising, again, that stellar feedback can prevent inflows or largely suppress inflows on these very large scales, especially in these low mass halos.
What is these reinizations? Nothing to do with
Reionization, the filtering mass is typically around here. It doesn't look anything like what you expect from photoionization heating, right?
What redshift though? This phase, right? So I think both high redshift.
Well,
we'll
so
put some more
here's,
detail later on.
yeah.
But
let's talk later. I don't think that's it. I don't think either the mass or the
It's
redshift
not a matter of
dependence.
speculation, right? You have the code, you can figure it out.
Yeah.
What is the reason?
We do, but fire simulations are very expensive,
I see.
right? Millions of CPU hours to rerun these simulations. Yes.
So at least for that simulation, it may not be general.
Yeah. These are fresh results, so we haven't had a chance to rerun simulations yet. Another assumption commonly made in SAMs is that you can eject material from the ISM. You can eject it completely from the halo, or you can only eject part of it from the halo, but that the outflows are not able to sweep up a significant amount of material from the CGM and push it out of the CGM. So this shows the cumulative amount of mass that's pushed out of the halo relative to the amount that's pushed out of that ISM shell. So in the SAMs, you can see it's always less than 1, but in fire, it can actually be greater than 1. This is cumulative, it doesn't look so dramatic, but locally, if you look sort of event by event, you see these large bubbles in the CGM, driven by stellar feedback, that can actually sweep up and push out a significant amount of mass from the CGM, and presumably that's also preventing inflows as well. Okay, as I expected, I'm going to run short on time here, but I can't resist showing you just a taste of this beautiful work. So there's a black hole working group as well within SMAUG, led by Daniel Angles Alcazar, who's an associate research scientist now at CCA and the University of Connecticut. So he's done something that he calls hyper-refinement simulations of black hole accretion. So he takes one of these Fire 2 simulations of a massive halo as a starting point. So already this has baryonic mass of around 3 × 10⁴ solar masses. And he follows it to a redshift of 2, and then he starts splitting the gas cells more and more as he goes in towards the black hole, so that he has increasingly better and better resolution towards the black hole. And then he can study how much material is actually captured by the black hole, just using direct gravitational capture. So there's no subgrid, Bondi or anything like that in these simulations. So you can see here the zoom going down to smaller and smaller scales, and you can see somewhere orbiting in here the little black hole. It's this little black X, and so we can study, according to the different conditions in the galactic nucleus, whether the black hole accretes very rapidly. So this is a near quasar phase of very rapid accretion, or later on we see very low level accretion. Turns out the black hole is here in a bubble that's been created by the stellar feedback. So here there's no feedback from the black hole itself. We're just trying to study how gas gets accreted by the black hole in the presence of gravity and stellar feedback. Okay. That was SMAUG. Of course, there's like 10 other projects that I don't have time to tell you about, so stay tuned. I want to tell you about some other work now, which is more along the lines of let's push forward our current models and see what we can learn. And so this is related to a problem that's, I think we've seen some interesting progress on recently. So we have a pretty good accounting of the cosmic star formation history and the buildup of stellar mass over time in the universe. But up until recently, we knew almost nothing about the history of gas accretion in the universe. So a few years back, starting in 2014, 2015, I started working with some collaborators on implementing recipes for estimating the fraction of the ISM in the form of cold dense gas, so sort of we label it molecular gas, versus atomic gas, sort of neutral atomic gas. And we used very simple recipes extracted from simulations. The basic ansatz being that molecular gas forms on dust, which is maybe tracing metals, gets photodissociated by the UV background, and forms more rapidly in dense regions. So we basically have a recipe depending on the gas surface density, the metallicity, and the local UV radiation field. And then we checked whether we could reproduce local scaling relations between things like the fraction of H1 or H2 to stars as a